So, I want to point something out. In our derivation, we could have kept this guy. Okay, how did we get that guy? It was V naught, generically it was V naught cosine theta, wasn't it? And then we still have the times t here. Then this guy was h, right? The initial height. What was 400 radical 2? V naught sine of theta. And then what does the minus 16 turn out to be? Or just the 16? That's 1/2 the acceleration due to gravity. Okay? That 16 is. So, and the derivation in general is not much harder if you use the stuff in purple rather than the particulars of this problem. So that gives us the generic formula down here for the path of a projectile that does ignore air resistance, right? And other important things. So R of t, in general, the I component, or x of t, is going to be v naught, the initial velocity, times the cosine of the initial firing angle, times t, and then the j component, or y of t, will be the initial height plus v naught sine theta t minus 1/2 g t squared. Okay, what are the possibilities for g here? So g could be either we'll use 9.8 meters per second squared, or g could equal 32 feet per second squared. And if your distance measurements in meters, you're going to use the first one. If your distance measurements in feet, you're going to use the second one. Okay? And I think that might actually help answer your question from earlier as well. Okay, so this is where A of t is negative g times j, right? Before we used 32, but in general it's negative g. And then the magnitude of v of 0 is v naught, and r of 0 is h, the initial height, times j. And of course, the assumption is that r of t is your path of the projectile. In the homework, I think all of the problems assume h equals 0 to keep things simple, which means the initial height is 0, which means you could solve some of these problems using certain kinds of symmetry. But what I'd like you to try to apply this formula when you solve it, not the related formulas from physics.